In this section, we're going to look at the idea of symbolic manipulation and symbolic variables in MATLAB. Generally, thus far, we've just defined computer science sort of variables to where they usually store a string or a double or a floating point, that sort of thing. But we haven't necessarily defined variables that can be operated on that just are placeholders for any generic sort of value. And so that's what a symbolic variable is. A symbolic variable can hold an expression, right? And instead of just a numerical value. And we can go ahead and manipulate formulae rather than having to work with a specific numerical value. To define a variable as symbolic in MATLAB, you're going to use this command, symsx, right? Now, if you wanted to just do a singular symbolic variable or symbolic command, you could use symx. If you want to make more than one variable symbolic simultaneously in the same line, you just put a space. And we're going to be able to substitute values into our algebraic equations or expressions, excuse me, and we're going to use the subs function. And I'm going to show you this in a few moments. But we can go ahead and just use subs and then whatever the function is defined as. So if this is x or fun or whatever it might be, the old variable and then the new value that you're substituting into the variable. We're going to start by taking a look at just some really basic numeric and algebraic operations. And so these are just some common ones. There's more than this that are in MATLAB, but these are probably some common ones that you might use to help you throughout your calculus sequence or to make things a little bit easier throughout your engineering physics classes, etc. And so we have expand, which is basically polynomial multiplication, factor, which is polynomial factoring, solving, and if it's possible to analytically solve an equation, then you just use the solve function, simplify, which might simplify a rational expression or a polynomial expression, whatever it might be, and then part frac, which is going to give you the partial fraction decomposition. So just as some basic examples of this, and I'm not even going to work on this example yet, I'm just going to work on the basic stuff. For example, we might have something to the effect of, and I want to do something basic first. So let's say we have 1/2 plus 1/3 to start, all right? And, we run this, and that's going to give us the repeating value of that, so 0.8333. But if we use sim 1/2 plus 1/3 and then execute that, it's going to give us 5/6, which is really cool that we can get an exact value or an analytic value rather than an approximate, right? If I say sim of pi, and usually if we type pi in, I'll type it up here, and I'll run it so we can see both the approximation and then we get the symbolic variable. So that's what a sim is. It just gives you the exact value. Now, if I just wanted to do some really basic stuff, I'm going to say sims x. So I'm going to define x to be a variable. And let's say I want to factor something really basic, such as like x cubed plus 1. Right? And x is a symbolic variable, so I'm going to run this. And we can see right here, here are the factors. All right. So now if I define this, let's say p is equal to factor. Now notice that this is in list form. All right. So if p is equal to factor, check this out. P2 is actually going to give us the second factor of this. And so if I were to do something like this, f print f, I could just say percent or maybe comma percent s as a string and close that. So I could do parenthesis percent s, close that, and then another parenthesis percent s, and then I could do a backslash n, all right, to go to the next line, and I could say p1 comma p2. This is actually pretty cool. That's how I can get it into the factored form. So MATLAB does a really good job with the symbolic manipulation. It's up to us to be able to put it into that factored form, right? If it's something that has, so for instance, let's say I have x to the 16th minus 1. I'll factor that. Now, clearly, there's more than two factors in here. whole bunch of factors in this. So what I could do is I could find the size of P, right? So I could say size P, comma 1, and I'm going to get rid of this for now because I don't want to factor it yet. And that's going to do a couple things. Right? Or I'm sorry, it should be size 2. Excuse me. That's going to tell us that there's 5 factors. So basically what it tells us is there are 5 factors. And then that way what we could do is we could say for I equals 1 colon size of P comma 2. What I could do is an F print F. And I could just say parenthesis %s. And I could just go ahead and say PI. And then I can end that, and then I can do an F print F and just a \n when I'm done. And notice I put it outside of the for loop because I want to make sure that when I'm done, I do the enter. I don't want to do the enter each time. Otherwise, then I'm just going to get 5 returns. Right? And I can go ahead and run this. And right here is our factored polynomial. So this size function can really help you when you're doing some of this analytic sim stuff to be able to format it really nicely. And when you guys do your assignments, you're going to have to use this method right here to be able to format things. So I wanted to show you all that really quickly before we went through and looked at any of the specific sorts of operations. Now, of course, some other things that we can see is that we can factor, we can solve, we can simplify, etc. So for instance, just showing you these really quickly, and I know we have a couple problems, and I am going to get to those. Let's say I have P is equal to something like quantity 2x plus 7 to the 4th power, and then I just want to expand P. So this one just goes through, and you don't have to use a for loop or anything. It just creates it as a single polynomial. So that's one of the things that you're going to have to work with MATLAB is you're just going to have to determine, does it put things in a list form, sort of like the factor function, or does it put it as a polynomial or in the expanded form? Okay, so for instance, part frac, let's say P is going to be equal to 1 over the quantity of something like, we'll do an easy one, x cubed minus 2x squared minus or plus x. And I want to do part frac of this. Suppress this. And when I go ahead and execute this, this one just goes through and puts it in the partial fraction decomposition. So you don't have to do any work for it. All right. So I would suggest that you run through these and see which ones puts them in list form and then which one puts them in the actual answer to where it's not a list. Okay. Now, I'm going to go ahead and work through this first example, and then I'll stop the video and work through the second example. But the first example is a pretty easy one. We just want to prompt the user for a function. So we're going to get a function in terms of x. We're going to solve it for the zeros of the function, and then we're going to print out the number of zeros and all the zeros. So this is that for loop super thing. Okay, so let me go ahead and I'm going to prompt the user. Okay, so I'm going to call it fun is going to be equal to input. I'm going to say enter a function in terms of x. And then what I'm going to do is I'm going to solve this function. So I'm going to say solve fun equals 0. Well, there's a couple things I could do. So one thing I could do is I could say equation EQU is going to be equal to when the function double equals 0. All right. So basically this first one is assigning the equation to EQU, and then fun equals 0 is just setting the function equal to 0. And then we're going to solve EQU comma, x. So that's going to solve the equation for x. Now I'm just going to go ahead and print that out just to show you what happens, whether it's going to be in list form or which form, like column form or list form. So I'm going to run it. And let's just say something really easy, like x squared minus 1. All right, so now notice it puts it in a column form this time. All right, so if I go through and transpose that, what I could do is I could just say size of, and if I wanted to, I could assign that to a variable. So I could go ahead and I could just say sol is equal to that. So that's our solution. So for instance, sol 1 and sol 2 are going to be the two solutions that are stored inside of the array. All right, so I'll run it again just to illustrate. So we have x squared minus 1 . And so notice that here's our two solutions. All right, so now if we had a higher order function, then we'd have to go through and we'd have to just say I, or we have to do a for loop. Okay, we don't want to sit there and do like, solution 5, 6, 7. That's just a waste of our time. Right? So we're going to do size of sol, and let's do comma 1. It's either 1 or 2. So you just run it. And I'm going to do it again, x squared minus 1. Oh. And so notice that the size gives us 2. All right, and that's what we're looking for. We're just looking for the number of solutions. All right, so now we know that when we're running our solve function, that we should say size sol comma 1 to figure out how many solutions. Okay, so if we go back to what the problem asks, because we do have a problem here. We want to write MATLAB code. We're going to get the user's function, and then we're going to solve for the zeros. Done. We're going to print out the number of zeros and the zeros. Okay, so let's go ahead and do that. Shouldn't be too difficult now. So we're going to say an fprintf, and we're going to say there are %d solutions. And we have our size of sol comma 1. So that's going to say how many solutions there are. And we're going to fprintf, and we're going to say the solutions are, and I'm just going to leave it at that because now I can make a for loop and print those. So for I equals 1 colon size sol comma 1, so that just says how many solutions there are. We're going to fprintf. I'm going to say a %f in here, and I'm going to print out sol I. And I'm going to end this. And then finally, I'm just going to do an fprintf of the return carrier. So that way I can just jump to the next line. So just some formatting stuff. Right? So let me go ahead and run this. And what I'm going to do is I'm going to put in a 4th degree polynomial. So let's say x to the 4th minus 1. And we know that there's a few complex solutions or imaginary solutions. So let's see what happens here. All right, so the 4 solutions are -1, 1, -0, and 0. And that doesn't make any sense because we know that 0 is not a solution to that. So check this out. I'm going to change the f to a %s, and I'm going to run this. And let's do the same thing. All right, and check this out. Now it gives the solutions, even the complex solutions. All right, so it may be helpful when you're doing this to use %s rather than %f or %d, because all you're doing is displaying, right? And we can put a comma in there, although the comma is going to put a comma after the last one, so it doesn't really matter. But we could just say x equals, no big deal. All right, so that's pretty cool. That's how we're going to work some of our algebra stuff. In the next video, I'm going to show you one more example of using all the algebra stuff together. But for right now, this should help you to be able to not only use the sim functions, but to kind of get an idea that formatting is a little bit important while we're doing sim functions.